Okay. For those that are back, welcome back. I am Mr. Oliver. I teach at Hayfield, and what I'm going to be doing today is I'm going to be going over experimental design is going to be mainly the thing I talk about today, but I'll happily answer any questions you may have. So I'm trying to get the notes. Give me one sec. So for those here, what we have first is, let's see if that's it. See if I can get this. Bear with me. I'm going to see if I stop sharing if this helps. Okay. I have notes from last week on describing, comparing distributions, and reading output tables and describing scatter plots. So let me see if I can get that to post. That's not going to be it. Okay, so then we're just going to go into it one at a time. So what we have first is from last week. When I was talking about that socks thing, if you look here, you should be able to open this. If someone could go ahead and try and open that link and just let me know if it opened for you. It's going to give me a thumbs up or a yes in the chat if it worked, or turn your mic on and say yes. Cool. Okay. That is on the next one I just put is describing scatter plots and reading data output tables. So those are the two things from last week. So let me just kind of walk you through what I have there. I made up these notes for my class and I feel like I want to share them with you. Basically, what it does is it allows you to kind of see the various things that you're going to be exposed to when you're asked to describe a distribution. So, for example, this is usually one of the questions. It's either going to be on this topic of describing and comparing distributions, or it's going to be on describing scatter plots. This is usually one of the four guaranteed questions. Oftentimes it's the first one, but it's not always the first one. So that's why I want you to, like, it doesn't always mean it's question one, but it's usually question one. So what I talked about last week is I talked about using this acronym SOCCS, SOCCS. That's how we describe a distribution. So the first thing we talk about is shape. There are three shapes we talk about: skewed right, skewed left, and roughly symmetric. It's kind of a rough picture of what they look like. I also added the picture of a uniform distribution so you can kind of see what that looks like. The big thing I wanted you to take away from this is please use the word roughly in front of symmetric. It just is going to be safer. The O in SOC stands for outliers or unusual features. This is, again, what we talked about last week, so you can kind of review. First C stands for center. Kind of talked about what the best measure of center is, but when provided a plot of data, median is an acceptable measure of center. Spread, and then context. And I said you always wanted to do context. And the idea is when you're asked to compare two distributions, use those phrases. So that's something we talked about last week. So now you can have a one-page reference on that. There was a folder up on our Schoology page that had this. I'm not sure where it went. I'll put it back up after today's lesson so that we have it. Also, my video about the other one was up there. I'm not sure where that went. I will find that and put that back up as well. So that's the first one we talked about. Next one we talk about is describing a scatter plot. And I said this is kind of the thing I recorded the video on. I recorded the idea of how you describe a scatter plot. And I went through this idea of these various aspects of how you describe a scatter plot. I won't go into too much detail because I want to kind of focus on experimental design today, but I wanted to show you that there's an acronym there as well. It's DOFS. It stands for direction, outliers, form, and strength. Again, kind of give you a picture and some visuals on that. The other part is, and I'll probably come back to this a little bit later, is reading this data output table. As you can see on this page, there's a lot of stuff you can read. So what I want to do is I'll come back to this later and I'll kind of explain to you how you read this one of these data output tables. Probably look at it on Sunday. Our next review is going to be on Sunday from 5 to 6, and I kind of talk about that a little bit. Okay, so those were the two that we talked about last week. What I want to talk about this week is I want to talk about the idea of collecting data in experimental design. So this is what we're going to talk about today. What I want you to understand is this is another one of the FRQs. So if you really want to think about it, let me come to my OneNote so I can kind of walk you through this. Let's do this. We are going to have the following. We are going to have one question that is going to be on DOFs or socks. So those two things I just went over. So there'll be one question that'll cover this. There will be one question on what we're going to talk about today in the idea of experimental design. There will be one question on probability and random variables. There will be one question on inference. There'll be one question on inference. So there's four of our six questions. There will be one question that they call multifocus. In other words, it'll be a little bit of everything above. I like to call it the fruit salad question. It'll have a little DOF socks, a little experimental design, perhaps, a little probability, a little inference. It won't go into the grand details on things, but it will kind of touch on little things. It'll be quite, kind of quick hit questions. And I'll be honest with you, this one usually does have a number. This one is question 5. If you really want to know, they usually put this on question 1. They usually put this on question 2. These two right here kind of flip-flop from year to year on questions 3 and 4. Those kind of bounce back and forth depending upon the year. I would say I think last year probability was 3 and inference was 4, but I think the year before, a couple of years before, it was flipped. And then there's going to be one question, and that is going to be our investigative task. And that is always going to be question 6. And that is always going to be the question that we need to dedicate the most time to. So what I said from last week is you're going to do 25 minutes on this question. You're going to do 65 minutes on these 5 questions. So what it means is you're doing about 13 minutes a question here. You're doing about twice the amount of time on this question right here. The main reason is, and again, we'll talk about this the day before the test. I'll go over the investigative task. Here's the reason I save it to last. You can't study for the investigative task. It's something that it is something that we typically have not covered in class. It's applying something that you learned in class in a new way. So it's going over something that perhaps we've talked about. The example I always like to give is we've taught you how to do a Z test and we've taught you how to do a T test. They may talk to you about an F test, and there's an F test in statistics. And what they'll do is they will say, hey, the F test is very much like the T test, except here's a few changes. And then it'll walk you through an example of it, and then it'll ask you to kind of do the F test. So the way it is that you're applying your knowledge of T test to then learning this new idea of an F test. That's an example of something that could happen. So you can't study for that question. There just is no studying for that question. It's applying something you already know, and we don't know what the topic is going to be about. So last week we talked about this and we talked about this. What we're going to do this week is we are going to this week focus on experimental design. Okay. So please feel free to interrupt me as we go through this. Like, again, stop me if I'm going too fast. Stop me if you need clarifications. What I'm going to tell you on this one is this is a unit that is literally all definitions. There's one little picture towards the end, but I'm going to be honest with you. This is a definition focused one. So just to make it easy, because I've already kind of shared, let me go back to the chat. Let's see what we got here. So let's see if this works now. If not, I'll try something different. So let me try Control C, see if it works. Nope, not gonna work. Okay. Being stubborn today. Okay, so again, here are the notes that we are going to be working on today. If you want to save this link, print it out, make a copy, do whatever you want. That's what we're going to talk about today. These are these experimental design notes. Okay, so here's the deal. Experimental design. What I want you to notice is I want you to notice that it is a lot of vocabulary. It is a lot of definitions. So what I mean is when you see a question like this on the test, you're oftentimes going to be asked to identify what the experimental units are, what the control group is, what the factors are, what the levels are, these kinds of things that we're dealing with. So it is really, do you know a definition and how to apply it in a given situation? So let me use an example here. We're not going to go directly to the question, but what I'm going to use is the question to kind of tie us to these definitions. So, statistically significant, just so you know, this is the whole foundation of this course. We're trying to discover statistically significant information. Basically, this is information that is observed that is so unique that it wouldn't happen by random chance. So in your class, I'm hoping your teachers have taught you about the p-value and a p-value of 0.05. I'm hoping this rings a bell with some folks. That's when we're talking statistically significant. We're saying that if something were to happen by chance less than 5% of the time, and we end up with that result. So we go and we gather information and we end up with a result that only would happen 5% of the time by random chance. We have a statistically significant result. In other words, something's going on that we weren't expecting. Therefore, maybe whatever we're investigating might have some credence, some belief. Okay. So now, first and foremost, you need to know the difference between an experiment and an observational study. You need to know when you look at something whether you have an experiment or whether you have an observational study. So the idea is when you look at a scenario, the big difference between the two is this phrase right here, imposes treatment. In an experiment, we are doing something. We, the experimenters, we, the person doing the research, are doing something and seeing if something happens. So here's the question from last year. Aphids are tiny insects that feed on plants such as cabbage plants. A farmer wants to reduce the number of aphids in a cabbage field. A river is located 100 meters south of the cabbage field. The farmer divides the field into 25 regions of equal size, as shown in the diagram below. Each region has approximately the same number of cabbage plants. So there's farmer's house. Here's here's this farm, divided it into 25 plots, about 100 meters in a river. The farmer would like to estimate the proportion of cabbage plants in his field that are affected by aphids and believes that the extent of the damage is greater for regions that are closer to the river. To obtain an estimate, the farmer is considering three sampling methods. So again, if we look at the sampling methods, we want to see, is this an observational study? Is this an experiment? So the first sampling method says we're going to select a region which is closest to the farmer's house and farthest from the river, examine every cabbage plant in the region for aphid damage. So I would ask you, did he do anything to it, or is he just observing something? What do you think? Is Yeah, he's just looking. He's not like, here's the deal. This is an observational study. If this was an experiment, what would be is perhaps he would go and he would spray like one of these blocks with some sort of insecticide and another block he would not. And then he would look and compare the difference between the two. That would be an experiment. So what we're dealing with here is we're dealing with an observational study. We're dealing with an observational study. Okay. So that is oftentimes a question. So going back to kind of these definitions, we could be asked the question, is this an observational study or is this an experiment? And in a case like this is an observational study because we're not imposing a treatment. Okay. So, since it's an observational study, let's kind of talk a little about this and some of the things that happen in observational studies. And we'll look at the question and kind of work our way through it. Observational study observes items or individuals and measures the variables of interest, does not impose a treatment. Usually the phrase you're going to have is randomly selected. That's the phrase, randomly selected, random sample. You'll see those phrases. When it's an experiment, it's randomly assigned. Okay. These are just definitions you're going to potentially see on a multiple choice question. For example, retrospective, if something's retro, it's old. Retrospective is when we look backwards. I start right now and I look back and I investigate data behind from the past to see if I can observe something in the present. Prospective, I start here and I follow you through college. You're a senior, you're graduating. What I'm going to do is I'm going to survey you every year of college. And at the end of college, I'm going to try and draw some conclusion about what happened with you, and that's a prospective study. I have not seen it make its appearance in FRQs recently. It will occasionally make an appearance in a multiple choice question. So it's just kind of a definitional thing. Observational studies are typically done with surveys. Okay, so here is the deal. We're talking sampling methods. I'll come back to things in a moment. So we're going to talk about our sampling methods. So what we do in statistics is the following. When we do something in statistics, we want to do it randomly. The whole idea of random is it eliminates the idea of bias. And let me kind of explain to you what I mean by bias. Bias means systematically favoring a specific outcome. So, in other words, the example that I like to use in my class is this. I teach AP statistics. If I were to survey people in my AP statistics classes, I would be introducing a bias towards students in higher level classes because I'm only surveying people who are taking a high level class. So someone sitting in an Algebra 1 classroom couldn't be part of my study. So I have a bias away from Algebra 1 students. That's what bias means. So whenever you talk about bias, you're going to talk about the direction of the bias. There's always a direction. It's towards something or it's away from something. So anytime you see a question that references the concept of bias, that's how you want to think about. You don't want to think it's not like prejudice because that's the times you hear the word bias. What bias means is systematically favoring an outcome. So there are some methods that could be introduced to you that are bad methods. So let me go back to this question so I can kind of explain to you what I mean about bad methods. Let's take a look at this first sampling method. So the farmer's worried about aphids. The farmer believes that the aphids are worse closer to the river. Sampling method 1 says the following. He is going to go ahead to go to region 3, which is the closest to his house and farthest from the river, examine every cabbage plant in the region for aphid damage. So where he wants to go is he wants to go here. Let me kind of go back to my question because I can kind of draw on it a little bit better. What he wants to do is he wants to go to this region right here. He wants to go to that region. This is where he wants to survey. So, can anyone tell me what kind of issue might come into play with what he wants to accomplish and what he's doing with region 3? So, again, he wants to see aphid damage. He believes that aphid damage is worse closer to the river. What kind of issues has he introduced to his study in this case?
Isn't he only doing one cabbage field, just 3, which is far away from the river too?
Yeah, and why is that a problem? And this is like if you give the mouse a cookie, why is that a problem?
Because he's testing if the river causes damage to the cabbage plants.
Yeah, okay, so that's how you want to like don't perfect. That's how you want to attack it. Remember, always say like you if you've read the book, if you give a mouse a cookie, it's always like something that leads to something that leads to something. He did a sample of region 3, which is really close to his house. He believes that aphids are bad really close to the river. By picking this sample, he is not addressing his concern. So that's what the problem with something like this is. And that actually has a name. And the name of that is called, let me come down here. It is called a convenience sample. What he just did in this first case is he did something called a convenience sample. He opened his front door. He looked out his front door. He saw a plot of land right at the bottom of his steps. Because if we go back and we look at this thing right here and we look at his question, he literally walked out his front door and he picked something that was really easy, literally right out his front door. He did what's convenient to him. The example I give in class is this. If I were to ask you all to determine, let's say, study habits for the AP test, and I said, what I want you to do is I want you to go out and I want you to get for me some information from classmates about how much students have studied for the AP test in May. What I know majority of students would do is you'd go to the lunchroom, you'd sit down at your desk you sit down at the table in the lunchroom, and you'd ask your friends sitting at the table with you how much you'd study for the AP test. because it's easy. And that's a convenience sample, and that's not a good sampling method. You've introduced bias. You are not doing something randomly. You've introduced a bias to the situation. So that is an idea of bad sampling. So the first method here is a bad sampling method, and that's actually what the first question is. The first question says, explain whether sampling method one is an appropriate sampling method for the farmer to use to estimate the proportion of cabbage plants in the field that are damaged by aphids. Well, if I want to follow the logic, kind of like what Dylan said here, he believes that plots of land closer to the river have worse aphid damage. If he were to use this yellow highlighted region as his estimate, he would underestimate the amount of aphid damage. Because if he used this little plot to represent all 25 of these plots, according to him, he believes bad here. He is as far away from that river as he can get. He's going to get less aphids, so he's going to understate kind of his true aphid damage. Okay. Any questions about that?
Do we have to say underestimate or overestimate?
Usually you want to talk about the direction of the bias. Yes. I'm going to say not every question is going to give you credit for it, but anytime you're talking about something where it says, explain whether it's an appropriate sampling method and estimate, I would always kind of talk about over or underestimate what the bias would be in the direction. You should always talk about the type of bias and the direction. I'm not going to say they're always graded entirely, but I'd rather you put it down and not be used than you not put it down and it be looked for. And you're going to see that kind of follows through with all of these kind of methods, except for the next question as well, you'll kind of see what I mean in terms of that. So the answer is yes. I always hate to say this because it feels like I'm always telling my students to write more, but I don't know from year to year what College Board is looking for. So kind of let me show you what I mean. This is the scoring rubric for this question. So let me see if I can get this up here. So here's what we got. Okay, so what they were looking for on this question. So when you look at a scoring rubric, I need you to understand something. This is the model solution over here, right here on this side. No one ever gives this answer. So please don't expect that you need an answer a question that looks like this. They're saying it's not appropriate because it's a convenient sample. It's not selected randomly. If the farmer's belief is correct, there may be fewer cabbage plants. This may lead to an underestimate. What I want you to look at is how we look at it from scoring. What they were looking for first is that method one was not appropriate. So you wanted to say, nope, not good. Provides an explanation that refers to at least one of the following. That region is not likely representative of the entire cabbage field. There's no random selection, or the sample is a convenience sample. So as long as you said one of those three things, you got the next point. And the following point is provides context. And just as something you should know, context is going to be something that's going to follow you through every question. So what they needed you to do is they needed you to talk something about the region on the field. They needed you to talk about the population. They needed you to talk to you about the aphids that were there. So somehow we had to talk about cabbage fields, region 3, and aphid count, something along those lines. And that's what they were looking for on this one. Notice they weren't, in this case, looking for that underestimate part. There wasn't anything in here that really talked about the underestimate part. However, it's part of the model solution. So that kind of answers the question that was asked. Any questions there in that kind of first question? Okay. Let's look at the second one. So the second one is the following. Sampling method 2. We're going to randomly select one row, A, B, C, or D, D or E, and for every region in that row, we're going to examine every cabbage plant for aphid damage. Okay, so let's go and talk about what that question's asking. Using sampling method 2, the farmer randomly selected row E and examined every cabbage plant in row E. If the farmer's belief is correct, determine whether the selection of row E is likely to provide an over or an underestimate and justify your answer. So, what do you think? Would it be an over or an underestimate? If the farmer's right in what he's saying, would it be an over or an underestimate? Because he randomly picked that row. What do you think? Over or underestimate the amount of aphids on his plants?
It would be an overestimate.
And the reason why?
It's extremely close to the river.
But see, that's again, always give a reason why. Don't just don't answer just yes. You say overestimate because row E is closer to the river. And if the farmer is to be believed, that's going to be where you find the most aphids. So if I use that row to represent everything, I'm going to overestimate it.
Mm.
Does that make sense in terms like always don't feel like you got when it's especially when it says justify your answer, give a justification. I know you can say, well, when I look at the picture, Mr. Oliver, it's really close to the river, then say that. E is close to the river. If the farmer's right, E is going to have the most aphids. If all I use is E to estimate everybody, I'm actually going to run into a problem. The problem I'm going to run into is I'm going to overstate the aphid damage.
Oh, okay.
Does that kind of like follow the logic through? I the, the the problem I see is that students often say overestimate, end of story. When it says justify your answer, you got to kind of explain your thinking behind it. So let's talk about that scoring rubric. What it's looking for is three things. They wanted you to say it was an overestimate, and you had to hit all three. You have to provide a justification based on the location of row E is closest to the river. So what you initially said to me was, hey, it's an overestimate because it's closest to the river. You actually hit components 1 and 2. The piece that most students met was this idea of linking why it's an overestimate is because it's closer to the river and the farmer believes the river has the aphid impact more, it's going to be an overestimate. So that's the kind of the next answer. And that kind of goes back to this, where what we're going to talk about is we would be talking about our sampling methods. So realistically, what the farmer did there, just so you know, the farmer did a stratified random sample. Or I guess you could argue maybe he even did a cluster random sample. It'd probably be more of a cluster, and the clusters were the row. So yeah, to be honest with you, the more I think about it, I would probably say he did more of a cluster random sample. So why do we do clusters? The reason we do clusters is because they're easier. I mean, that's honest to God the answer why we do cluster samples. They're easier. It's a random process, but it's an easier random process. So that's what he did. He did a cluster random sample. So let's jump back. Any questions when it comes to that second question? Anything about the idea in that second question? Now, I'm pretty sure not all of your teachers, I know there's one person here who's heard this before. Not all your teachers here are going to give you this last one, and I'm going to really honestly be straightforward with you. If there's nothing else you take out of today, please take what I'm about to talk to in question C out of the way. So, sampling method 3 is randomly select one region from each of the rows A, B, C, D, and E. For each selected region, examine every cabbage plant for aphid damage. So basically what this guy is saying for this last one is we're going to randomly select one guy from every row. So what's going to happen here is I'm going to like say randomly pick 5 and then 9 and then maybe I get 15 and then I get 17 and then I get 24. Okay. What's good about that process? There is something good about that process. What is good about that process?
It's randomly chosen.
It's randomly chosen. Well, so is the green. Just so you know, the green was randomly chosen as well. So, yes, randomly chosen is important, and that's good. What else is good about that? Maybe compare it to the green. What is good about the pink that wasn't good about the green?
It's from every row rather than just one row.
So do you think you're going to get do you think you'll get a better estimate overall if I'm pulling stuff from like, each row?
Yeah. I would
Because
definitely.
if I average out really far to really close, the idea is theoretically that I'm going to be getting a better realistic view of this thing. So this guy, this is a random process. Okay. This is a random process. So the idea here is going to be interesting. It's not going to ask us why this is better. Watch what this asks us. It asks us to describe how to implement sampling method 3, which requires a random selection from one region of each of the rows A, B, C, D, E. Okay, now I'm assuming most of your teachers taught you like a random number table, taught you flipping a coin, taught you like something like that. Am I correct in that?
Yes.
Okay. Did any of your teachers teach you about this? And there's one student who's sitting in here right now who should know this. That is a baseball cap. I'm going to tell you that the big hat method is going to be a way to describe a random process that is going to get you the points and prevent you from running into some of the problems that students who don't use this run into. So the idea is this. Let's not talk about this question right now. Let's say that I wanted to pick a random person out of this class, out of this review session. There are 9 of you in this review session right now. What I could do is I could take a slip of paper and I could write someone's name on the slip of paper. So, I could go ahead and I could write Lincoln's name on a piece of paper. And what I would then do is I would write the names of all of the other ones of you, all the other ones in this class, the other 8 on another piece of paper. So what I would have is I would have 9 slips of paper. I would then take these 9 slips of paper and I'm going to go ahead and I'm going to stick them in a big hat. And here's the important thing when I put them in the big hat. I'm going to mix that hat up. I'm going to shake the hat up to make sure that the names get mixed in. I am then going to reach into the hat. I'm going to go ahead and take my hand. I'm going to reach into the hat. And what I'm going to do is I'm going to pull a slip of paper out and I'm going to see whose name's on the slip of paper. So, for example, that piece of paper might have the name Scott on it. Scott is now part of my random sample. That is a random process. Let me explain to you why it's a random process. All 9 of you went in the hat. The shaking of the hat made it random. Now, when I reached into the hat, everybody had an equal chance of being selected. So when I go to do this process, I'm doing a random process. So my recommendation when you are trying to talk about the idea of describing a random process, I want you to think about it in the big hat method. And the way, again, that the big hat method works is what you are going to do is, I'm just trying to find something real quick. Where is text box? Give me a sec. Do we have text box anywhere? Doesn't look like it. Okay, so I'm gonna just go ahead and I'm gonna type it out. This will be a little bit easier if I just type it out. Come here and talk about the big hat method. So here is what we got for the big hat method. What we're going to do first, we are going to write the name of each member of the population on an equal size piece of paper. Equal size. We are then going to place all of those slips in a hat. We are going to mix that hat thoroughly. We are then going to select a slip of paper from the hat. That individual is in my sample. I am going to then place the paper to the side I'm going to repeat the process until I meet my sample number. So if I put 100 names in the hat and I needed 10, I'm going to pick out 10 pieces of paper from the hat, and those are the 10 people who are going to be in my sample. That is a random process. Everybody had an equal chance of being selected. Everybody had an equal chance of being selected. The problem that students run into is they don't want to follow this random process. They want to kind of talk about random number generators. Here's the issue that you run into with the idea of that number process. When I number people, I got to remember things about numbering people. Here's one thing I have to remember about numbering people. Let's say that I had 10 of you in class. There's 9, but let's say that I had 10 of you in class. Here is a problem that I would run into. If I were to label you the numbers 1, 2, 3, 4, all the way up, and let's say I had 10 people in the class, I'm going to tell you labeling you 1 to 10 to use a random number table is not going to be accessible. Is not going to be acceptable. Here's the reason why. How many digits long is 1? How many digits is 1?
1 digit,
How many digits is 10?
2 digits.
There is a 1 out of 10 chance of me picking a 1-digit number. There is a 1 out of 100 chance of me picking a 2-digit number. These are not equal probabilities. So the first thing you have to remember is you have to remember that every one of these numbers should be the same number of digits long. So the first thing you got to remember is when you're using like a random number table, you got to label it 0, 1, 0, 2, 0, 3, 0, 4, all the way up to 10, because now it's a 1 out of 100 chance to be picked. Next thing we run into when we number people. What happens if I picked person number 17? If there's only 10 people and I pick number 17, I have to say I'm going to ignore it. I also have to address what I'm going to do with repeats. This is a challenge you run into when you do a random process using a random number table. There's a lot more things you got to keep track of. Whereas the big hat method doesn't have that problem. I have 9 equal sized slips of paper, or 10 if we added one extra person, 10 equal sized pieces of paper. All the paper are the same size. I put all of those paper in the hat, I shake them up. I don't have to worry about picking 17 because there's only 10 names in the hat. And if I take a piece of paper out and I read that number or that name off the piece of paper, what I can then say is I've addressed about repeats and stuff because I've taken the piece of paper out of the hat. Does that make sense in the way I'm explaining it? I just want to make sure.
Yes, but would we not need to like account for like with or without replacement?
That's why when we take that piece of paper out of the hat, we say we don't put it back in.
Oh, okay. Okay.
If you notice when I said we take the piece of paper out of the hat, we place it to the side. We literally are taking, it's almost like we're drawing names out of the hat, and we're taking advantage of the fact that when we imagine just the visualization, if you were to do this in class, you would literally take the name out of the hat, you would read it, you'd put it down on your desk, and you'd go back into the hat to get the next name. That's kind of how you would do it if it was you. So that's how you want to describe it. And the big hat method always kind of works. It does give you a proper, like, random sample. Okay. So let's talk about here, because this is going to be kind of a modified hat. If I want to randomly select a, a, a piece or a region from this grid, how many hats do I need? How many rows am I selecting from?
Five
According to the
rows.
instructions. Yeah, I'm selecting from 5 rows. So what I would do is I would have 5 hats. I'd have a hat that was A, I'd have a hat that was B, and I'd go all the way until I had the hat that was E. Which numbers would go into the A hat?
1, 2, 3, 4, and 5.
Which would go into the D hat?
16, 17, 18, 19, and 20.
Okay, so what I'm going to do is I'm going to place those 5 numbers into each one of those hats. Please mix the hats. Please mix the hats. Please mix the hats. Please mix the hats. Here's the reason. If I were to put the numbers 1, 2, 3, 4, 5 into hat A, do you know who's the most likely to be picked? Is piece of paper 5. Because piece of paper 5 was the last one in, it's sitting on top, most likely to be picked out. Whereas when I shake the hat up, it's not going to be the case. I'm going to be mixing the slips of paper around. So I put the numbers 1, 2, 3, 4, 5 in hat A. I shake it up. I select one region from A. I put the numbers 6 to 10 in hat B. I select one number from hat B. I repeat the process. I get to the end. I put the numbers 21 to 25 in the hat. I go ahead and I do one number and I get a region. And in that case, what I'm going to get is 1, 2, 3, 4, 5 regions. Okay, now I'm going back to giving the mouse a cookie. I have now selected the 5 regions. What do I do now? Because I got my 5 regions. I got 5, 9, 15, 17, and 24. What do I do now? What's the point of this whole exercise? What am I trying to do?
To compare the aphids in the cabbage field and to
So
test
I
if
need to
it's
count. I need to count the aphids in that region, right? So basically, you know what I need to do? I need to do what he says right here. Examine every cabbage plant for aphid damage. What I need to do now is, now that I have selected the 5 regions, I need to examine all 5 of those regions for aphid damage. And like you said, compare them. So this is again the thing, like when you're asked to describe a design process, the way I like to explain it to is explain it to me, explain it like you were telling your grandmother how to do it. If you were explaining it to like, hey grandma, here's how I want you to do this. I want you to take a box. I want you to put the numbers 1, 2, 3, 4, 5 in a box. I want you to shake up the box. I want you to take a piece of paper out of the box. I want you to note what number that is. I want you to repeat the process for the other 4 rows. Okay, you got 5 numbers sitting in front of you now, Grandma. What I want you to do is I want you to go out to the field, go to that region, count how much aphid damages each one of those regions, and compare them for me. That's what the process is. That's how we describe a random process. I'm going to tell you the big hat method will work. Oftentimes, other methods add extra extraneous things that you need to consider in there. And what I really want you to understand is you need to be aware of all the little nitnoid things you got to keep track of. What I want to show you is I want to show you an example, and I graded this paper. I graded this question. So what I want to show you is this. Okay, so what I'm going to do is I'm going to go to the 2024 test, and I want to go to the same question that was on this one, and it was this question right here. So let me zoom in so let me make it a little bigger so you can see it. Okay, so here's the deal. Background on this question is the following. This guy wants to determine if the auto drive feature of a car reduces your gas mileage. What he wants to do is he wants to look at 70 different days to and from work, and he wants to have 35 days with the autopilot and 35 days without the autopilot. So here is how the big hat method works. I'm going to take a big old hat. I'm going to put 35 slips of paper that say auto drive in. I'm going to put 35 slips of paper that say no auto drive in, or I'm going to put 35 papers that say yes, 35 that say no. I'm going to shake that hat up, and every morning I'm going to grab a slip of paper out and I'm going to read it. And then when I read the slip of paper, that's what I'm going to do when I drive the car. That is a random process. Can anyone tell me again why? Okay, let's talk about the idea. Could I have done this with a coin? Could I have done this with a coin flip when I flipped a quarter? Like, can you think of a way you could explain it to me on how I could do this with like a quarter? What would I do if I wanted to do this with a quarter? How many outcomes do you have when you flip a coin?
2 outcomes.
Okay, so what do you want heads to be? Driving with the autopilot or driving without the autopilot?
Driving with autopilot.
Fine. Okay, so I flip a coin. If I get heads, I drive with the autopilot. If I get tails, I don't drive with the autopilot. What does it say I want to do? It says I want to get 35 days of each. So you want to know what the most common mistake the students did was. Here's what they said. I'm going to flip the coin and drive according to whatever one of those rules are until one of the groups is 35. And then I'll just drive the rest of the days with the other thing. Here's the problem with that. Those last days never had anything random done. They were automatically defined already by the situation. So those last few days, so let's say I hit autopilot 35 on day 62. That means 63, 64, 5, 6, 7, 8, 9, 70. Those next 7 days, I'm driving without the autopilot. Those 7 days were not random. Here's why the hat is random. In the hat, when I start, all 70 days are in the hat. Every single one of those conditions had an equal chance of being selected the first time. Once I took the first one out, they all had the same chance of being selected the next time, the next time, the next time. So let's say I went through and when I selected 62 numbers out of the hat, I was done with autopilot. Yes, I understand that the remaining, 8 numbers in that hat all say the same thing, but those 8 numbers have been in the hat since the beginning. Since they've been in the hat since the beginning, we actually do have a random process. So, if you're ever asked to describe a random process, I want you to please use the big hat method. The only modification you may run into is you may have to do multiple hats, like we did in this case with A, B, C, D, E. We had to have 5 hats. Does that make sense in terms of understanding a random process?
Yes.
Okay, I'm going to be honest with you. This is how you should describe a random process. Yes, there are ways to get it the other ways. I am telling you, a hat is going to always work as long as you do the following. As long as the slips of paper are equally sized, as long as you mix the hat, and as long as you say what you do with that piece of paper once you're done with it, you've described a random process. Okay, so that's the idea of the big hat method. And I am telling you, that is going to be a lifesaver when it comes to describing a random process. Now, I know your teachers have probably taught you the random number generator. Random number generator works, but you got to kind of keep track of a little bit more. Random number generator is nice in the sense that if I tell my random number generator, give me 10 numbers between, or give me 35 numbers between 1 and 70 with no repeats. Yeah, that's good. That should work. That should give you an acceptable one. But the idea, there's sometimes little kind of minor things. The hat method is always going to work. If the pieces of paper are the same size, if they all go in the hat, if the hat's mixed up, and if you say, when I take it out, I put it off to the side and go to the next, that's that with or without replacement thing. So if you take nothing else out of this hour-long thing, please take the big hat out of this thing. So, any questions at all in general about some of this stuff? So let me give this link for anyone who came in late. Copy link. So anyone who came in late, this is today's notes. That's today's notes. I'm going to put them up in the Schoology group as well. What I do want you to understand is we also have, for those that popped in a little bit late, this is from last week. This is from last week. So those are our ones from last week. So what I now have done is, let me go back to this. This again, definition, 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 definition. So what I would do is I kind of scan over this and just kind of look at the different definitions that you'll see here. So what we do is we have about 10 minutes left. So if does anybody have any questions as you kind of scan through these about any of these definitions that you might want me to talk about?
Can you go
Don't
over
worry about the, go ahead.
can you go over confounding variable? I don't totally understand.
Okay, yeah. It's an appropriate name for a variable. Okay, here's what a confounding variable is. A confounding variable is something that we often is going to be tied to both the explanatory and the response, but sometimes we can't kind of control for it. So, for example, let's say I was introducing to you a new way to work out that was going to improve your cardiovascular conditioning so that you could run longer. Okay, so I'm going to come up with this new exercise plan that is going to help you run longer and faster. So when I'm looking at this, the treatment I'm imposing is this new kind of running method or this new kind of way of exercising. So visually, if I wanted to deal with it, what's going to happen is this. It's like, you got the person here and I want to teach them how to run. So what I'm going to do is I'm going to introduce this program to them. And at the end of, say, 12 weeks, what I'm going to measure is I'm going to measure how fast they run. Okay, so that's my experiment. However, there is things that could confound here. Let me explain to you some things that could confound. Age could be a confounding variable. Someone who is 15, 16, 17 years old is more likely to be athletically sound, maybe able to kind of develop an athletic skill a little bit better than someone who's, say, 55 years old. Age could be confounding there. Another thing that could be confounding there is the person's diet. Okay. Let's say that, I got two people who are running. This person eats a vegan diet. This person eats pizza for dinner every night. Do you think that that could have some bearing on how the program affects them?
Yeah.
Yeah, that could be a confounding variable. Okay. Running experience could be a confounding variable. What it's saying is that, hey, does this program work? How fast did you run to start with? How fast did you run to end with? We want to see you running faster here. Well, age, diet, running experience, it could all be confounding variables. They're variables that are tied to both of them. Your running experience is tied to this. Your running experience is tied to this. The food you eat is tied to the running before and tied to the running after. But that's not something that we are controlling for in a process. That's what a confounding variable is. Okay. We would know about that. Let me contrast that with something called the lurking variable. And let me tell you something that I could show you research on. There's something I could show you research on that is 100% true. The more TVs you own, the older you live. It's proven. If you own more televisions, you live longer. The people who own more television sets also have a longer life expectancy. So I can now conclude that televisions lead to longer life expectancy, right?
I don't think so.
No. Well, what am I missing here?
I'm sure there's like some
What do you think
other,
happens? What do you think happens if you own more TVs? Give me a reason why you might own more TVs.
maybe you're wealthier. like in
And
a higher,
if you're wealthier, what does that mean when you start to feel sick? What are you going to probably do?
better healthcare and better. Yeah.
There you go. That's the lurking variable. Lurking variable is something you weren't considering that plays a big role in it. The one that they oftentimes, and I don't know if your teachers have ever done this, you do realize that ice cream sales and people drowning are strongly correlated. The more I have ice cream sold, the more I have people drowning. So I should stop selling ice cream if I want to have people not drowned. What's lurking there?
People drowning is probably because it's summer, and that means you're selling more
And
ice cream.
there you go. The lurking variable summer. That's something I didn't consider. This is one of these guys. What a confounding variable is, it's a variable that I know exists, but I can't really do anything to kind of control for it. So confounding is I know it's there. There's really nothing I can do about it. So I just kind of address that it's there and I go through with my research. A lurking variable is something that I wasn't expecting to be there. That's actually the reason why something's happening. Did that help?
Yeah.
Okay. They do ask questions about confounding. I will tell you, they do ask questions about confounding. They'll say, hey, what could be a confounding variable in this experiment? And that's the kind of thing. You have to come up with something that would say, like, if it was the running thing, you would say, well, someone's running experience is going to be a confounding variable because someone already knows how to run might not get as much of a return as someone who's never run before, kind of thing. Any other questions from these? Any of these other kind of statements that we got here? Anything else you want me to talk about? Any of these? I'm gonna scroll through them. Let me look and see. All of these are good questions for also for question 5 for the multi-focus fruit salad question. These are all valid kind of things you'd see there. Different types of biases. Yep. Okay, let's talk about the different types of biases. That'll kind of like be the last thing we do. Okay, so the most common ones are the ones you need to know about. Convenience sample. You do what's easy to you. You do what's easy to you. It's going to have a bias in the direction of those who might share similar opinions. That's a convenience sample. Voluntary response. Voluntary response is another type of bias. What that is when you let people choose whether or not they're going to participate in your study. The reason that's a bias, strong opinions. If you've ever been on an internet site and you've seen like a poll there, you know who's the only people who vote in the poll? The strong pros and the strong antis. The people who don't care, don't vote. Their opinion matters too, and you never get it. That's what's voluntary response. Undercoverage is another type of bias. The easiest example I can give you for undercoverage is homeless people. If I'm doing a study, homeless people are almost always undercovered because how do you get a hold of a homeless person? They have no address. They typically have no phone number. They don't have a mailbox. How are they going to get in my survey? So that's an undercoverage. Non-response bias. It's exactly what it sounds like. The people don't respond. There's 2 types of non-response bias. First one, you look at your phone, you see it says spam caller polling. You hit ignore. You just are a non-response bias. You chose not to participate. Here's another example of non-response bias. They try and call your parents during the workday at home on your home phone. They're non-response because they're not there to receive it. So we're a bias away from those opinions. Response bias. Easiest example of response bias. I have like 9 of you sitting in here. Give me a thumbs up if you've ever cheated on a test. Most of the time, I'm not going to see any thumbs ups, even though someone may have cheated on a test in the past. That's a response bias. You're saying what the person wants to hear. You're lying, in other words. And then wording bias. I use the same example of wording bias all the time. Let me ask a question for all of you all. Do you think the government should restrict your constitutional rights? What do you think? Do you think the government should restrict your constitutional rights?
No.
No, right? Most people say no, right? Okay. In the light of all the school shootings we're seeing, do you think that there should be stricter gun control laws?
Yeah.
Okay, you do realize, okay, that no and no, that's fine. But you do realize when you say no, I don't want the government to restrict my constitutional rights, but yes, I want stricter gun control laws. You just gave me a conflicting answer. Because a stricter gun control law would be restricting your constitutional rights. And it's really how I word the question influences the answer. And that's what wording bias is. Wording, here's the example that I always love to give. You guys know all of these stupid surveys you all have to fill out, right? All of these endless surveys you have to fill out in class, like the SEL surveys and all of these things, right? Have you ever wondered why those comments you read sound like so gobbledygook? They're that you read them and you're like, I don't even understand what this thing is saying. That's because it's trying to eliminate the wording bias. They don't want to influence your response to the question by using words that are strong one way or another. And that's what wording bias would be. And those are the types of bias you need to know. There's others, but those are the types of bias you need to know. Any other questions for me? Okay, here is the